Thank you, everybody, for joining. We have with us Dr. Faisal Akram, who is an associate professor of physics at the Center for High Energy Physics, the University of Punjab. He works in quantum chromodynamics and associated low energy effective field theories. He's here to talk to us about LHAASO, an experiment which his group has recently joined. He is heading this effort at CHEP. So over to you, Faisal. It's always a pleasure to have you. Thank you for accepting our invitation to come.
Thank you, Rizwan. As Rizwan has told you that we have recently joined an experimental collaboration, nuclear physics, and it looks very odd that a person from a theoretical background is joining an experimental collaboration. You would see the reasons that why we have to do this thing. So probably most of you know that what are the cosmic rays? Cosmic rays are non-thermal population of the particles that prevails in the universe, and it includes proton, helium, and almost all other elements. However, elements above Ferrous are very rare, and space observation indicate the existence of electron, positron, and antiprotons as well. The cosmic rays are almost isotropic, though we observe some anisotropy at a very high energy, but at low energy, these are isotropic. And the flux of the cosmic ray obey the power law. And this power over here, that is called the spectral index. And the origin of the cosmic ray is still an open problem in physics. And the reason is that why it is still an open problem, because they are isotropic. We don't have the specific sources from where they are coming. And that's why we don't know that what is the exact source of this cosmic ray. Although we have some idea that probably the gamma burst and pulsars, they interact with the galactic material and the cosmic ray charged particles that produce scattered in all directions. But these theories are not yet verified. Perhaps the most important observational property of the cosmic ray is the energy spectrum and its composition. The plot which you are seeing here, that is actually based on hundreds of experimentals which have been performed in cosmic ray physics, including both ground-based experiments and space-borne experiments. And we have precisely measured the flux of the different compositions. And this black curve, that is called all-particle spectrum. When you just measure the energy and just ignore the composition of the cosmic ray, the spectrum which you get is that is called the all-particle spectrum. And the total flux of the cosmic ray from 1 JeV to 10 raised to power 11 JeV is 10 raised to power 4. And if you just look at the all-particle spectrum, you see that there are some interesting features. First of all, we observe a knee over here, and then there is another knee over here, and this is the ankle. We call it ankle. So what is happening at these knee? That somehow the value of the spectral index is changing. For example, at this knee, the spectral index changes from 2.7 to 3, and then at this knee, it changes from 3 to 3.3, and then there's a significant change at this point as well. So the second thing which we would like to discuss is that as far as the flux is concerned, this is the observational property which we'd like to know. And exactly, the question is that how exactly we measure this flux. Okay, let's first talk about this thing. To precisely measure the flux of the cosmic ray, we have to measure three things. We should be able to measure the energy of the primary cosmic ray particle. Obviously, it's a flux of energy, so we must have to measure this energy. We also have to measure the direction of the primary cosmic ray particle, and we also have to identify the type of the primary, whether it's a proton, helium, or which type is it. And currently, there are two different types of experiments which are being used to measure the cosmic ray flux. The first, as I said, the space-borne experiment, in which we have a detector, which is primarily a calorimeter, which is orbiting some in some orbit, and the cosmic ray particle comes in, deposits the energy, and all this energy is collected, and this is how we measure its energy. And the way the cosmic ray particle deposits energy, that has certain features. From these features, we can identify its type, and we can also identify its direction as well. But since these space-borne detectors have a very small size, relatively small size, so therefore the detectors saturate when a cosmic ray particle of energy greater than 1 TeV hit it. So we can't use these detectors to precise measurement of the cosmic ray flux above 1 TeV. So that is the reason that we have the ground-based detector. And what happens in the ground-based detector? In this case, the Earth atmosphere itself acts as a calorimeter. So you can think of it as a giant detector in which the atmosphere is acting as a detector. And when the primary cosmic ray particle enters in the atmosphere, and then a shower, a cascade of secondary particles is produced, this cascade is called extensive air shower, which I will discuss in more detail in the coming slide. And most of these secondary particles which are produced in this shower, they are absorbed in the atmosphere. In a very small fraction of the particles, secondary particles arrive at the ground level, where we have an array of the detector, and we detect them. So we are not able to measure the whole shower in this case. We can only measure a small fraction of the shower. And from this measurement, we are required to identify the energy of the primary particle. And we are not only required to identify its energy, we are required to identify its direction and identify its type. So in this case, the task is far more complicated than what we have in case of space-borne experiment. And what is the advantage? The advantage is that there is no saturation. We can measure the cosmic ray particle as high as possible in the nature. And currently, if you just go back to this, look at the spectrum, and you can see that where the spectrum is ending, that is 10 raised to power 11 GeV. Just to remind you that in Large Hadron Collider, we accelerate the particle. A proton is accelerated with the most sophisticated accelerating technology only up to 7 TeV. So it's thousands of magnitude high. So this is what is the advantage of the cosmic ray physics. It allows us to study the particles. It's a high energy particles which we'll never be able to study them in collider physics. I will make some interesting comparison later on. But the real challenge is that how from the fraction of the measurements, we are able to reconstruct the energy, direction, and identify the type of the primary particle. So here is a simulation of the cosmic ray shower, which is produced by a proton of energy 10 raised to the power 14 electron volt, which means 100 TeV. And you see that the first interaction occurred at an altitude of 20,000 meters, that means 20 kilometers. And then you have a cascade of the secondary particle. Most of the secondary particles are being absorbed in the atmosphere in a very small fraction, arrive at the detector, which is detected by this detector array. Okay, so this is the size of the shower of proton of energy 100 TeV. Now you can imagine that what would be the size of the shower of a proton of energy 10 raised to power 11 GeV.
Just out of curiosity, what are the secondary particles?
What are
the secondary particles?
I will show them later on in more detail, but here you can refer to this code. The blue lines, they are the hadrons, and the gray lines, they are the muons, electrons, and then the green one, these are the neutrons. Okay. So I will talk about this composition later on in more detail.
The lower axes are also in kilometers?
Yeah, they are in meters. Okay. So you see that only this part of the shower is actually being detected, and this is confined within 1 kilometer. So that is the reason that if you want to study such a big shower in a ground-based detector, you require a very extensive array of detectors.
So the proton bumps into air molecules and is produced.
If the primary is a proton, the proton is actually,
in this case it's
The primary could be something else as well.
It can be something else. So it interacts with it doesn't actually interact with the air molecule. It doesn't see the molecule, it sees what is inside the molecule. Okay, so it's interact with the hadrons inside the nucleus of these molecules. So from this, all these secondary particle properties. So this is another animation in which we are showing we are removing those particles which are absorbed. In the previous slide, I show all the particles, okay? But those which are absorbed in the atmosphere, they are removed. So this gives us entirely a different view of the shower. So shower is developing in such a way that you see that there are no remnants. They all are absorbed in the atmosphere. And on this plot, you can see that how the shower is developing. As the altitude is decreasing, the number of charged particles in the shower, they are increasing. Then we attain a shower maxima, and then the charged particles starts decreasing. And at the ground level, you can see clearly that we are not actually measuring or detecting all the charged particles which are produced in the shower. We are only measuring a fraction of them. And from this lower plot, maybe I should show this animation again. This is how the composition of a different secondary particle is changing with time. And at the ground level, this is right now, the plot is at the ground level. Most of the particles which arrive at the ground level, they are electrons. And then we have the muons, and then very few hadrons and neutrons. So the shower which is arriving at the ground level, that primarily consists of electrons and muons. So that is the reason that when we are developing a cosmic ray detector, we should have an array of detectors which can efficiently detect electrons and muons. Okay, we don't have to detect hadrons, other hadrons, or other particles in the ground-based detector. And this is just one more animation in which the shower development is shown in 3D. And it's interesting to see that the shower is slightly concave. It's not flat. And it is also interesting to observe that when this shower hits the ground level, the timing is very important. Because if you have an array of the detector, the different particle will be detected at a different time. And this information will be important in order to reconstruct the direction of the shower. Okay. So I will not go into this detail. Mostly I will talk about the energy reconstruction, but I'm just using this animation to see that why we require this timing information is important to reconstruct this direction. Okay, so this is again, I think, 100 depth shower. Yeah. Okay, there's interesting contrast between the cosmic ray physics versus the collider physics. In collider physics, we accelerate the protons, and currently we can accelerate up to 7 depth only, right? And then we they target each other, and from this, the particles are produced, and our detecting technology is so sophisticated, we can track each of the particle which is produced through this single interaction. And this is so precise that if you, and now you can not only identify the track of each of the particles which is produced from a single proton-proton collision, you can precisely measure its energy, its momentum, and you can also identify that which type of this particle is. So you have a complete information of the collision event. But in the cosmic ray physics, we don't have such an information. You have a high energy proton, it interacts with the proton, it produces thousands of particles, but we don't have any information of this track. Unless we someday will be able to build a gigantic detector, particle detector, and we bring it to the upper atmosphere and we could record everything. Then it will be possible to go the energy beyond, far beyond the 7th depth, okay, because there is no limit of the energy in the cosmic wave physics.
Sir, how these particles attain millions of depth energy in the first place?
This is still a mystery, that how these particles attain this energy. We can just guess about it, but there's no clear picture that how these particles attain this energy. And I said that the primary reason is that the cosmic rays are highly non-directional. So we lost the information of their sources. Okay, so this is the cross-sectional segment of the cross-sectional view of ATLAS detector. And there is something which is happening in this detector, which is actually the analogy of the what we are observing in the shower. You see that there are different layers of this detector. Inside we have the silicon tracker. Its purpose is just to track the direction of the particle. And then we have the layer that is called electromagnetic calorimeter. And then we have the hadronic calorimeter. And you see this is a small cascade which is being produced in the hadronic calorimeter. It's exactly the same thing which is happening in the whole atmosphere in case of cosmic ray physics. So there are interesting comparison between the cosmic ray physics and the collider physics. Okay, so let's see that how we understand this shower, because without having a clear understanding of this shower, we cannot reconstruct the energy or cannot reconstruct the identity of the primary particle by the fraction of the measurement which we are doing at the ground-based detector. All this shower, the animation which you have seen in the previous slide, they have been produced by a software which is called Corsica. The Corsica is actually implementing our complete understanding of particle physics to produce the simulation of this shower. If I just show you the PDG book, so every number which is written in this PDG book, that is actually used in the Corsica. Okay, so let's see that how this Corsica works, because it gives us some deeper understanding that how this cosmic ray shower is actually being produced. So it all begins with the primary of a certain energy, okay? And as it enters in the atmosphere, it undergoes the first interaction. And the distance which it will cover before the first interaction, that is called the interaction length, which is equal to the reciprocal of the cross-section of the proton with the air molecule. So if you have measured the cross-section of the proton with the air molecule in the Large Hadron Collider, you can use these cross-sections to calculate the first interaction, the first length, the length which the particle will cover before the first interaction. Obviously, at Large Hadron Collider, the measurements are up to 7 meters. So we have to extrapolate these values through different hadronic models. Okay. So what happens that after the first interaction, and this is exactly the same kind of collision which we are producing in Large Hadron Collider, the hadrons are produced, the muons are produced, and then electromagnetic particles are produced. Inside the Corsica, we treat the hadrons in a different way, muons in a different way, and the electromagnetic particles, they are treated in a different way because they behave in a different way in Earth atmosphere. So these hadrons, they still have a very large energy, and they can further interact with the air molecule, just like the first interaction. Or if they don't have the large energy, they will decay. Okay, so when they will decay and when they will further interact, that depends that what is the decay length of this hadron, which is produced. If the decay length is less than its interaction length, it will decay. And if the interaction length is less than the decay length, then it will interact. And this interaction, the decay length is constant. It is just defined by its decay constant, but its interaction length is changing with time. As its energy is decreasing, because the interaction length depends on the cross-section. The cross-section is a function of energy. So as the energy of the secondary hadron is decreasing, its interaction length is actually...
So why is it losing energy if it's not interacting?
Why it is?
How is it losing energy? What is the energy loss mechanism for the...
Yes, we have to implement at this interaction. When the first interaction is occurring, we have to simulate this whole interaction. Okay? The cross-section is just telling us.
So you produce the hadron.
Yeah.
Why would it lose energy if it doesn't interact with something else?
No, it will not lose the energy. It will lose the energy through the interaction.
Okay.
So in the Corsica, we don't just simulate this process that the interaction length is changing with time. We simulate the interaction itself. So we simulate all the particles which are produced in this interaction, apply the law of conservation of energy, and that's how the energy of the secondary.
But then why is the interaction length changing with time? That's my question.
Because the secondary hadron is a lesser energy than the primary hadron. So when the hadron energy is changed, its cross-section is changed, and that changes the interaction. That's how it is.
Right. So, but you're just saying that different secondary hadrons would have different interaction lengths.
Because they have the different energy.
Yes.
Yes.
But that does not mean that the interaction length is changing with time.
No. in a single interaction, you will have many hadrons. It's
Yeah.
not a single
Fair
hadron.
enough.
They have a different energy.
Sure, sure.
These hadrons will interact once again with the air molecules.
Right,
So the energy will be further more
so-
distributed.
So I guess
as
what
the
you're
net-
saying is,
Yeah.
I guess what you're saying is that tertiary vertices are
Yes.
formed at different lengths. That's what you're
Yeah,
saying.
yeah.
Okay, fair
Sort
enough.
of.
That makes sense.
Okay, so this is how we do it. And when we decay, we incorporate all decay processes which we have observed. And there are hundreds of thousands of the decay processes you can see inside the PDG, which are incorporated, but those having the branching ratio less than 1%, they are excluded. So what about the propagation? So what happened during the propagation? So you have one interaction, then another interaction. Okay, so what is happening during the propagation? The Corsica, during the propagation, we incorporate the loss of energy due to the ionization. The particle is still ionizing the air atoms, so there will be loss of energy. There will be Coulomb scattering, Cherenkov radiation, which will be emitted. All these losses are also incorporated during the propagation. So what about, this is how the hadrons are described. What about the electromagnetic particles? So the evolution of electromagnetic particle, in this we incorporate bremstalling, Moeller scattering, Baba scattering, annihilation, and in case of photon, we include pair production, conference scattering, photoelectric interaction, and so on and so forth. Whereas in case of muons, we incorporate bremstalling, pair production, and decay process. Okay, and again, the idea is same. Interaction is produced according to its interaction length, which depends on the cross section. And during the propagation, the loss of energy is incorporated through ionization and other losses. So this is how this whole shower is simulated. So coming back to the interaction, we usually apply two different interaction models, high energy interaction model, because these interactions are described by quantum chromodynamics, which is theory of strong interaction. And at high energy, QCD is perturbative. So we have perturbative interaction model. At low energy, it is non-perturbative. So we have non-perturbative interaction model. So we can change this cut that where you go from high energy interaction model to low energy interaction model. Okay, so let's go to the LHAASO. I think you have enough knowledge to appreciate that what is happening inside the LHAASO or what kind of detectors we have there. So this is an overview of LHAASO. LHAASO stands for Large High Altitude Air Shower Observatory. And this is located at Chengdu. I'm sorry, I'm saying it correctly. Yeah. I think very close to the Tibet area. So it consists of 3 detectors. There are 3 independent detectors. So it's not just a single detector array. We have 3 different detector arrays for different purposes. We have WCDA, that is Water Cherenkov Detector Array. And this building which you are seeing here, that is WCDA building. It contains 3 pools of water. And the cosmic ray, the secondary electron and muon, when they pass through the pool, they produce Cherenkov photon, which we measure through the PMTs. And then we have the KM2 detector. So this is the area of the KM2 detector. We have several hundreds of arrays of electromagnetic and muon detector. Electromagnetic detectors detect electromagnetic particles, and muon detectors detect muon particles. And these arrays are shown in this schematic diagram as well. And then we have WFCTA, Wide Field Cherenkov Telescope. This is an interesting part of it, and I think it's not a well-established detection technology, but it's an experimental-based technology. So what we have, when the cosmic ray particles are moving in the atmosphere, they will be producing Cherenkov radiation. So these will be the high energy photon, which will be arriving at the ground level even before the shower itself. So we can see the shower even when it is in the atmosphere, before even arriving at the ground level. So WFCTA, this has been designed to detect these Cherenkov photons so that we could get some information about the shower which is arriving towards the Earth. But our group is mostly focused on WCTA and KM2 detector. So in the physics goals, we have obviously the cosmic ray physics. Want to measure the spectrum as precisely as possible. Then we have a gamma ray astronomy. We have the sources of this, like Crab Nebula, for example. The Crab Nebula is producing electromagnetic radiation. So by just detecting these electromagnetic, and they are high energy, they have enough energy to produce the cosmic extensive ray shower. So we can actually see the Crab Nebula through this facility. And not only the Crab Nebula, we can see other gamma ray pulse and other gamma ray sources. So gamma ray astronomy is also one of the physics goals. Search for dark matter, that is also the physics goal, but my group is primarily working in the cosmic ray physics. So let's talk about the KM2 detector. It consists of two types of detector array: electromagnetic detector, muon detector. They are 5,216 EDs and 1,188 MDs. And they are separated. Each is has a surface active area of 1 meter square separated by 15 meter, whereas the MD, they have a bigger area, 36 meters square separated by 30 meter. It's just a repeat. So they are actually not covering the whole surface, okay, because detectors are located in the discrete positions. So they are covering a fraction of the surface where the shower is arriving, and that fraction is 0.005 in case of EDs, and in case of MDs, it is 0.05. So let's just quickly look at the details of the EDs and MD. Inside the ED, a single array, we have a scintillator, and when the electromagnetic particles passes through the scintillator, the light is produced, and this is collected to the fiber optics, and from the strength of the signal, we measure the energy of the passing particle. Whereas in case of muon detector, we have a water tank, and in this case, when the particle enter it, muon will enter in this muon detector, Cherenkov radiation is produced, which is collected by this PMT, and from the strength of the signal, we measure the number of muons. So in short, I would say that ED and ED will count the number of electrons which are arriving at it. And similarly, the MD, muon detector, will count the number of muons which are entering in the detector. Okay, so let's see that what is actually the shower event and what we are recording. A shower event is composed of many EDs and MD hits. And a hit means that some signal is being produced. And each hit has a timing and the charge information. And the charge information is related with the number of electromagnetic particles and the number of muons. So we combine this information, the timing information and the number of the amount of the charge which is collected. We combine this information with the position of the EDs and MDs. And from this data, we can construct the primary direction. We can easily construct the primary direction. We can easily locate the core location. Core location means if the cosmic ray particle is coming, it is producing a shower. What if there will be no shower? Where the cosmic ray particle will hit? That is called the core location. Okay? But the real challenge is to reconstruct the energy of the primary particle and identify what type of primary it is. And for this, we require a Monte Carlo simulation. A Monte Carlo simulation of not only extensive ray shower, but also the Monte Carlo simulation of detector itself. So Monte Carlo simulation of extensive ray shower and detector response. So we have, the LHAASO group has developed this Monte Carlo. We have produced a large number of Corsica events, and they're very expensive to produce. I have told you that in a single shower, thousands of particles are produced. So if you want to produce a single event, it may take us several minutes to produce it. So by using the computing resources available in IHAP, Institute of High Energy Physics, China, we have produced 10⁻⁷ Corsica events in the energy range from 1 TeV to 30 PeV. Remember that Large Hadron Collider can operate up to 7 TeV. And we have produced a simulation for different components: proton, helium, CNO, magnesium, aluminum, silicon, and the ferrous. And we have a detector response simulation software, which is G4KM2A. And then we have to construct the events, software for constructing the events. But let's just see that what kind of data is available to us once we have apply all these softwares. So the data, an event consists of a certain data values. And in the data values, we have the total number of electromagnetic particles detected by the detector array, total number of muons detected by the detector array. These are the global information about the event. But then we have some special information, because each detector is recording the number of electrons and muons independently. So we have this information, number of electrons and muon for each ED and MD respectively. We reconstruct core position, and we also save it in the data, because we don't even need any Monte Carlo simulation to reconstruct the core position. We can use the data itself, and we can reconstruct the core. We can also use the data itself to reconstruct the direction of the primary, so that is also stored. And then we have stored the time of the event in the form of modified Julian date. The true energy of primary and its type, that is something which we have to investigate, how we can determine, reconstruct the true energy, or we can identify its type by using the data which is recorded in the event.
Why 1 TeV as a lower limit? It's already beyond standard model.
Yeah, because I'm asking that why I'm starting from 1 TeV. Why not lower than 1 TeV? Okay. So what happened that I think I missed that point. The showers having energy less than 1 TeV, they are not the big enough to produce any effect at the ground level.
They get absorbed.
Yeah, they are completely absorbed in that. So that's why we started from 1 TeV.
Then the real QCD is like gone.
Yeah. I mean, it's non-perturbative QCD is gone, but it's not actually gone. You have the,
There is no QCD.
it's a primary energy, 1 TeV, primary energy. It will produce the secondary hadrons.
Okay.
And
There's work for you to do. There's work for you to do.
Secondary hadrons.
I'm happy there is a job for me.
मैं समझ रहा था आप LHC के साथ कहा रहे हैं LHC तो already ये 1 TeV.
Okay, so what we do to explore that how we can reconstruct the energy and how we can reconstruct the primary, we study the response using the Monte Carlo simulation. We study the response of any versus the true energy. How the true energy means the one which we have stored in the Monte Carlo simulation, how the true energy varies with any. And this response is almost linear. But its intercept, that depends on the primary. Okay, so you see that if you have a shower in which they are 2.5, 10 raised by 2.5 number of electrons, then the primary energy for the proton is lowest. Okay, and the primary energy for the ferrous is higher. So there is some information in this graph that the size of the shower depends not only on the primary energy, but it also depends on this component, its type. And this is the response of muons. And this is also show the same thing, that the response not only depend on the energy, but it also depends on the type of the primary, right? And since it is linear, so that means that in the log scale, it is linear. So it will be following the power law. And for proton, when we fit it with the power law, the coefficients, I'm sorry, the power is, in case of Ne, it is 1.046, and in case of muons, the power is 0.9. So the slope is almost equal to 1, but not exactly 1. Okay, so we can also, once we understand that how the proton is, the response of the proton, we can also guess about the response of the heavy elements by using superposition principle. So what we can understand it like this. So think of proton, and we know that what kind of response the proton is producing. Now let's think of a ferrous, or maybe just let's think of a helium. Now, in case of helium, you have 4 nucleons. In case of proton, you have just 1 nucleon. So In case of helium, you have 4 nucleons, so it means that the 4 nucleons are simultaneously interacting with the air molecule. So that means in case of helium, you actually have 4 proton showers superimposed upon each other. Okay, so in this way, if I apply the superposition principle, then I can guess about the response of any where A is the atomic mass number for heavy element for elements other than proton. And similarly, I can guess the response about E as well, and that is consistent with this result. So the data actually shows that the superposition principle is applicable. Okay, so let's play with some numbers. Okay, now assume that this is the response of NE, and this is the response of NU. We are here assuming superposition principle as well, and A is the atomic mass number of the primary. It's the value of A through which we can identify that which primary it is. And the response is not only the function of energy, it is also the function of atomic mass number of the primary, right? And that's true for NU as well. So let's play with these numbers, these rules. So let's take a log on both sides. We have 2 equations, and then just take a linear combination of these 2 equations. We get this equation, okay? And on the left side, you have the numbers which you are measuring in the detector. On the right side, you have the energy and the type of the primary defined through A. Now, these coefficients, A and B, are arbitrary. We can choose them. Let's choose them in such a way that this factor is 0. And this factor is equal to 1. So you are imposing 2 conditions. From these 2 conditions, you can fix these 2 constants. And once you impose this condition that this factor is 0 and this is equal to 1, you are left with this result. So it's interesting. So that means that no, you can construct the energy from the available information without knowing that what type of primary is it. Okay. And then we can play in another way. For example, what if I take this as 0 and let's take this as a 1? Now, in this case, you again can calculate these coefficients A and B, and you find that the resultant formula will give you the A. So from the same data, the number of electrons and the muons, you can calculate what is the atomic mass number of the primary. So that's very simple. But that's not that simple, because this is based on the mean response of the detector. So these equations tell us that how the detector will behave on the average, but how it will behave in a single event, these equations are not telling us anything about it. So the results which you will be generating from this, they will be buried under the huge statistical fluctuations in the data. Anyway, but still we have interesting results. But if we apply them, maybe I show you in the next plot. No, I think this plot is missing. Okay. There is another way of looking at the shower. I mean, right now we are discussing that how the shower information can be used to reconstruct the energy and its type. This is just one way. Okay, but there can be another way. And that is based on some model of the shower. That's what we call the Heitler model of electromagnetic shower. So how electromagnetic shower develops. So it starts from a photon and it produces electron-positron pair. And then this electron or positron that produce a photon. So we have 2 kinds of splittings. And these splitting operates recursively. And in this way, a shower is developed, right? So the question is that when this shower will halt, when this expansion will stop. And that would happen when we reach the critical energy, where the loss due to the radiation, where the radiation energy loss becomes less than the loss due to the ionization. So that means that in this case, this critical energy is 85. So the interaction length, radiation length in this 37 gram per centimeter cube. So that means that so what is happening? That when the cascade is occurring, the energy is distributed. Then another recursion of cascade, energy is further distributed. So as the iterations are going on, the energy is decreasing. And eventually the energy will be less than 85 MeV and the cascade will halt. So the question is that when the cascade will halt, then the total number of electromagnetic particles that is simply given by the total energy which has been deposited in the atmosphere divided by this critical energy. Okay, this is any maximum number of particles which you get. But beyond that, what happens? The particle will be still losing energy. They will be absorbed in the atmosphere. So till they reach the ground level, there will be some attenuation factor. Simulations show that this attenuation factor is of order of 10. So this implies that the total energy which is deposited in the atmosphere due to electromagnetic interaction, that is related with the number of electrons which we are observing at the ground level through this equation. So G is 10, and this parameter is 85 now. Now, something similar can be said about the hadronic shower as well. So here we have another model, which is called Heitler-Matthew model of hadronic shower. It is based on the assumption that when high-energy cosmic ray particles interact with the atmosphere atom or nucleon, then I said earlier, the hadrons are produced. Okay? Muons are produced and electrons are produced. But the muons or electrons which are produced, they're very small in number. Mostly the hadrons are produced. There are hundreds of the hadrons. Which hadrons are produced? 99%. The hadrons which will be produced, they will be pions. So it's a good approximation to make this assumption that when a single interaction occurs, then the pions are produced. So we have 3 pions, pi plus, pi minus, they will produce in an equal proportion. So these pions further interact, charged pions further interact, and again the pions are produced, and then these pions further interact, and again the pions are produced. So the shower is actually evolving through the charge. It is not evolving to the neutral pions, because the neutral pion, pi naught, that immediately decay into the 2 photons. And these 2 photons will be giving rise to 2 electromagnetic showers. Okay, so this is a very simplified picture of the shower which we are observing. So based on this model, we can tell that how much energy will be deposited in the atmosphere through the hadronic interaction. Since we know that what is the critical energy where the hadronic interaction stops, and that is 20 JeV, so if I divide it with the total hadronic energy, I will get the total number of muons. And the reason that why I will be getting the total number of muons, because all the pions, the charged pions, ultimately decay into the muons. Okay, when the cascade will halt, the decay length will become shorter, and all these pions will decay into the muons. So the number of muons which we will have in the shower, that is precisely equal to the number of charged pions. So that is the reason that from this we can estimate the number of muons. So the total energy which is deposited in the atmosphere, and that is the primary energy, that is some of the energy deposited through electromagnetic shower and some of the energy deposited through the hadronic shower. And the energy deposited through electromagnetic shower is related with the number of electrons, which we are observing at the ground level. And the hadronic energy is related with the number of muons, which we are observing at the ground level. And if you just play with these numbers, then you find that this energy, which is the energy of the primary, is proportional to Ne plus 25 Ne. So this 25 is a magic number. Okay, so if you multiply the number of muons which you are detecting with 25 and add the number of electrons, then your energy will be proportional to this factor. And that will also be composition independent, because there is no A factor which is appearing in this equation. So this is the estimator which we have recently used to study the flux of precision measurement of cosmic ray flux, which I will discuss in a moment. So, but first let us look at the response of this estimator. This estimator is represented by any mu. And this is the response of this estimator to the Monte Carlo. I think I just recall you this response. This is the response of Ne. The response is not only depend on the energy, but also on the composition. But the response of any mu, as you can see, is a composition independent. Okay? And there's something more for us. The last plot, you see, I said earlier that is the mean response. Okay? But actually, when you will reconstruct the energy through this formula, it will be distributed about the true energy. because of the statistical fluctuations. So the question is that if I take the difference of true and reconstructed energy, what will be the mean value of this difference? That is what we call the bias. And when we calculate the bias for this estimator, we find the bias remains 0 for all values of reconstructed energy. And then usually this, when we produce a histogram of this difference, the difference between the true and the reconstructed energy, it's a Gaussian. So you will have a sigma, which will be corresponding to the resolution of your energy. And this central plot that is giving us the energy resolution of this estimator. So energy resolution is relatively high at low energy, and then it's significantly decreased. But it's a bias which is more important. The bias is 0. Okay, so far we have been talking about this detail that we can reconstruct the energy by using the Monte Carlo simulation. Okay, but the Monte Carlo simulation is based on models. So what is the guarantee that these models are correct? Because if there's anything wrong with the models, your reconstruction will be absolutely wrong. So there has to be some absolute method for energy reconstruction or for the calibration of the detector. For example, the way we do in Large Hadron Collider, we pass the particle of known energy, we measure its energy, and then generate the detector response, and then that's how we calibrate it. But how we'll calibrate it? Because there's no direct way to measure the energy of the cosmic ray particle, right? But there's a way which we can apply. We use moon to calibrate the response of the detector. So that's an interesting dimension, how the moon can be used to calibrate the response of the detector, energy response of the detector, and that will be model independent, which will not be based on any Monte Carlo simulation. So what happens that the moon, first of all, produces a cosmic ray shadow. The cosmic ray particles which are coming from the direction of moon, they will be blocked. So if you just look at the data in the window about the moon, you will see a deficit there. And this is precisely what you are seeing in this plot. And the significance of this deficit, this is a significance plot. The significance is as high, I think 48. It's a very high significance. Okay, this is called cosmic ray moon shadow. And if you just look at carefully, you see the moon position is exactly at the center. Okay, we have fixed set the coordinate in such a way that the moon is at the center, but the shadow is slightly displaced. It is displaced westward. Can someone guess that why the shadow is displaced westward?
Due to the mutual rotation of Earth and
No. Cosmic ray shadow is displaced. It is displaced because of the geomagnetic force. The cosmic ray particles, they are actually move over the curved path because of the geomagnetic field. Okay, so the cosmic ray shadow is displaced slightly, and this displacement depends on the energy of the cosmic ray particle. So that's why by measuring this displacement, you can reconstruct the energy of the primary particle without relying on any Monte Carlo simulation. But unfortunately, this can be done only at low energy, not at a high energy. The reason is that simulations show that the shift which is produced by the shift which is produced by the geomagnetic field, that is inversely proportional to the energy of the cosmic ray particle. And this energy is in the TeV. For example, think of the proton, for which Z is 1. So if you have a proton of energy 1 TeV, then the shift will be 1.59 degree. And if you have a proton of energy 10 TeV, the shift will be 0.15 degree. We can measure these shifts, but if the energy is 100 TeV, the shift will be 0.0159 degree, which is impossible to measure it. So that's why we can calibrate the response of the detector by the cosmic ray shadow only over the TeV scale, from 1 TeV to few hundred of TeV, but not beyond that. And this is our group which have recently done it. We have used the cosmic ray shadow to to calibrate the response of the detector. I don't go into these plots. All you can see that these are 6 plots for different bins of estimators. Lower bin mean low energy, high bin mean high energy. And you can see that here the shift is highest, and then it is progressively decreasing. And here, this is the plot which shows that what is the reconstructed energy. Here, the black points are those which we have calculated by measuring the shift without relying on the Monte Carlo simulation. And the blue points are those which are generated from the Monte Carlo simulation. And we find an excellent agreement between the black and the blue, the orange points. That means our Monte Carlo simulation is correctly calibrating the response of the detector. Of course, this is being established only at a low energy from 1 TeV to 250 TeV. But once we are sure that our detector is, Monte Carlo is behaving correctly from 1 TeV to 250 TeV, so we anticipate that it will also be correct at energies beyond that. And once we are satisfied that our Monte Carlo is good, then we can go towards the precision measurements of the cosmic ray spectrum. So I know these are just few last slides where I will discuss the results of the flux measurements. So we use any mu as an estimator, okay? Because since this estimator is composition independent, so therefore the histogram of the energy, the constructed energy, that will give us the all particle spectrum, because we are not doing any particle identification. We are just correctly calculating the reconstructed energy. So the resultant spectrum will be the all particle spectrum. So we apply some event selection criteria. We select only those events which are within this zenith angle range, 10 to 30 degree. We apply some course selection, 320 to 420 meter. Only those events will be selected which are within this ring. Why this course selection is important? So suppose that you have a cosmic ray shower over here, okay? So this shower will partially be outside this region, but even it is outside, it still will be detected because there is a detector arrays there. If I extend this region and suppose that I use the whole region to count the events, and imagine that there's a shower over here, then this shower will be inaccurately be measured. Only the half of the shower will be measured. So this is called the edge effect. So to reduce the edge effect, we restrict our course selection into this smaller ring. And the shower strength is taken 20. We will select only those showers in which there are at least 20 electrons. And this is the plot which show us the efficiency of the detector. I don't go into the details, but I just want to highlight that once this response is flat, it means your detector is 100% efficient. No, not even a single event is being missed by the detector, okay? And this flatness comes at about an energy of 250 TeV. So beyond 250 TeV, with this event selection criteria, our detector array is fully efficient. And once we have meet these conditions, then we tune the parameters of our response. I already discussed in the previous slide that we make a linear fit of the energy and any mu. And the fitted values, they actually depend on the Monte Carlo simulation. Okay. And the Monte Carlo simulation, in the Monte Carlo simulation, we have different choices. We can change the interaction models used in the Corsica. We can change the composition models. And when we change these models in the simulation, we get slightly different values of these parameters. So we have some degree of composition dependence and some degree of interaction model dependence as well. So this is the final result. These red points, they represent the measurement of the flux, okay? The base on the 1 year data, yeah, September 2021 to December 22 data.
Flux of everything.
Yeah, the flux of all particle spectrum, ranging from about 300 TeV to about 20 PeV. Okay. And there is no statistical error. There is a shaded region that represents the systematic error due to the choice of the interaction model and the choice of the composition model, which I discussed previously. So these are very precise measurements. Okay. And what we discover is a knee there. That is actually the first knee. The people already know that there is a knee there, but we have been able to precisely locate this knee. So what we do that once we have this data, we fit it with the broken power law. Okay. So that broken power law actually modeled this response that the spectral index is changing from one value to the other value. This change is smooth. The gamma 1, that's the value of the spectral index before knee, and gamma 2, that these are the fitted value. Fit data with this model, and gamma 2, that is the value of the spectral index after the knee, and EB is the position of this knee. And if you just look at this number, it is 3.67 PeV. But it's more important to look at the error in this number. The first error is a statistical error, which is less than 1%. And the second is a systematic error due to the choice of the interaction models and the composition model, and that's a 5%. So by using this array of the detector, and we have been able to achieve this accuracy that we can measure an energy, a scale of energy with such a high accuracy. That is the scale where this knee is occurring. And the knowledge of this scale is very important because when the knee is occurring, it is indicating a change in the source of cosmic rays. Okay, so this number is crucial, and precise measurement of this number will be playing an important role in the coming studies on the origin of cosmic ray particles. Okay, so there are some preliminary results as well, which are exclusively produced by our groups. We are also using this detector, KM2 detector, to measure the spectrum at a very low energy. Okay. The reason that we want to go in this region is that in this region, the space-bound detector, they have very precise measurements because they can precisely measure the flux. So in this way, we'll be able to compare our results with those obtained through the space-bound experiment. And what we have discovered in our results, these are our results, there is another mean at an energy of about 300 TeV. This is the knee which we are seeing it for the first time. But these are the preliminary results. We are still developing them, and we don't know what would happen with this knee.
Maybe you want to call it a chin or something. You have two knees and an ankle. You have to.
So thank you very much. Finally, I would like to say a few words about this, the collaboration which we have initiated. We started this work, I think, about 3 years ago. This is my colleague, Dr. Mohsin, who did his PhD, not in LHAASO, but he did his PhD in study of cosmic ray tracing method and
sun shadow.
moon shadow. But you did work on
Sun shadow.
sun shadow. I mean, the cosmic ray not only produce moon shadow, cosmic ray moon shadow, the sun also block the cosmic ray particle. So we also see the deficit of the cosmic ray from the direction of sun. And that's more interesting because by studying this deficit, we can tell about the changes in the magnetic field which are occurring at the surface of sun. Okay, so we started this work because he has some connection with people which are working in the LHAASO. We used these connections and we started working with them, and eventually we were given acceptance to join this collaboration, I think a year ago.
23.
And we are 4 members, 4 or 5 members, 1 member, if I also include Ali, who's in China, then there are 5 members. So being a part of this collaboration, we have some advantages. We have remote access of all the data collected by LHAASO and computing resources. Okay, so we don't require any computing resources. We just we can remotely submit our jobs and get the results. Okay, so which obviously our PhD students and MS students, they will be using this facility to complete their related projects. They will also share the technology which will be used to develop the particle detector. In fact, we have a long term goal that we will have a cosmic ray experiment in Pakistan. We can't have a collider physics experiment. It's so expensive, so sophisticated that no country can have it. But we can have a cosmic ray physics experiment, and India already had it. They call it CRAPES. It's a cosmic ray physics. It's very easy to build. And I mean, the advantage is that you can easily scale it. So you start with a few rays, you double them, and then you triple them, and eventually you have a full-fledged research facility which you can study all these cosmic ray physics. Okay. A single ED or MD, they're not very expensive. So we have a long-term goal that eventually will, in collaboration with the other institute, we will head towards it to have a cosmic ray physics experiment. And the other facility which our students will be enjoying is the collaboration would offer local hospitality and stipend for 6 to 12 months. Stay at LHAASO, IHAB China, for jointly supervised PhD students. So any student who is in the joint supervision, he will learn the basic skills there. And when he is in a position to do the final analysis, the collaboration will host in China, okay? And they will also provide them the stipend as well. But in fact, this last point, that was actually the reason that I'm leading this project. I'm a theoretical physicist. I don't work in experiment, but I mean, the reason that I'm doing is not that I'm very competent, because cosmic ray physics is very easy. And this data is not as sophisticated, as complicated as that of a collider physics experiment. So anyone can learn it, okay? So that is precisely the reason I'm leading this group, because you see that we have a lot of problems with the issues with our PhD programs because lack of funding. So I think that with such a facility, we'll be able to attract the talented students to join the experiment collaboration of LHAASO. Thank you very much.
Thank you.
ये वैसे अच्छी टर्म है, local hospitality. Is always हम डाल सकते हैं attract करने.
Actually, मैं आपको बताऊं, जब मैं पिछले साल मैं जब चाइना गया था उनसे ये बात करने के लिए, तो मैं इसमें मुंह से ये अल्फाज नहीं निकल रहे थे कि मैंने कहूँ कि आप हमारे स्टूडेंट को लोकल हॉस्पिटलिटी प्रोवाइड करें. वो कहेंगे यार ये कैसे लोग हैं, हम इनको कोलैबोरेशन दे रहे हैं, डेटा दे रहे हैं, एनालिसिस करें, लोकल हॉस्पिटलिटी क्यों मुझसे मांग रहे हैं. तो मैंने डरते डरते ये कह ही दी उससे बात. एंड मैंने उससे ये नहीं कहा कि आप उसको स्टाइपेंड भी दें, मैंने कहा आप सिर्फ उसको लोकल हॉस्पिटलिटी दे दें. He said that we also provide him the stipend. अच्छा, फिर बाद में मैं सोचता रहा that why he agree so easy. तो मेरा फिर अंदाजा ही था, वो ये था कि वहां पर देखें जो PhD स्टूडेंट हायर किए जाते हैं एनालिसिस के लिए, PhD स्टूडेंट्स को आप कम से कम 5 साल स्टाइपेंड देंगे, और वो काम जो 5 साल स्टाइपेंड देकर उनको मिलेगा, वो सिर्फ 6 महीने का स्टाइपेंड देकर उनको मिल सकता है इस तरीके से. So
They need mathematics.
Yeah, that's not the only reason, I would say. I mean, they have a lot of funding to
yeah,
attract,
of course.
to basically build soft power and that. And that's how it should be. So very good, excellent. So do we have questions, Steve?
Yes, sir.
Yeah, please.
सर हमें कैसे पता चलता है कि कोई यानी कि 10 की पावर 10 जैम या इस तरह के कोई पार्टिकल ही तो रैंडम है, तो हम के लिए यानी कि जो ज्यादा हाई पावर वाले हैं वही हमारे ज्यादा काम के हैं, तो हम के लिए क्या करते हैं कि
What we do is that obviously we don't measure the energy. I said earlier, we measure the number of electrons and number of muons. And then we have a formula through which we can reconstruct the energy. And this formula is showing that there is a linear response. As the energy is increasing, as the number of shower size is increasing, the energy is increasing. So we cannot precisely measure the energy, okay? We can just measure the mean energy. But because there's some energy resolution, and you can see that at a very high energy, the resolution is 5%. So that means that if you are measuring for example, a shower of say energy 10 PeV, then the error in its energy, which we'll be estimating, that will mainly be 5%.
So, sir, has there ever been a particle in the Planck range ever? The Planck range.
Okay, so just look at this plot. This is the experimental plot based on hundreds of experiments. Look at where it ends. Actually, the plot doesn't end it. We have measured the flux up to that point. Okay. It's a 10 raised to power 11 JeV. It means it is 10 raised to power 7 TeV. Okay, because we always, particle physicists always think in terms of TeV. So it's a huge energy. You can never ever have it in a collider physics experiment. But there are limitations. I mean, the limitation is that the collider physics are important, not only because they have energy, they are important because they have luminosity. I mean, for example, think of Higgs particle. Its energy, its mass is 125 TeV. 125 JeV. It doesn't mean that whenever you will have energy of 125 JeV, you will be able to produce the Higgs particle. Actually, if you will have this much energy, then you will have to make 1 billion attempts, and in one you will be successful. Okay?
Statistically,
Yeah.
if you're lucky enough.
Yeah. So
Hypothetically, sorry,
please, it's all.
hypothetically, if you put, so you have muons and electrons hitting your detectors on Earth, right? And the cosmic rays are coming. Hypothetically, if you could reconstruct it, right? Would you say that the implication might be that we would understand what's wrong with the standard model? Like the missing pieces?
I think if we are doing the cosmic ray physics with the current technology, then the only way to test the standard model is through Corsica. Yeah. The Corsica, where we are implementing the high energy interaction model and the low energy interaction model as well. That's the only way to test it, indirectly. So you have some predictions of the model, you put it in the Corsica, and then you see that how well you will be able to describe the response of the shower with Corsica.
Yeah.
That's highly indirect. It's highly indirect.
Even in the Monte Carlo simulation, like assuming that you code in the standard model, right?
Yes.
And assuming that you can reconstruct it, now you will be following the approximations from the standard model in your Monte Carlo simulation, right? So obviously there is, I mean, it's a big if, obviously, but if you could, then you would be able to tell, right? I mean, the need for a bigger detector to collide particles at a higher and higher energy.
No, I don't agree with it.
Okay.
Cosmic ray experiments are not alternative to the collider physics. They are complementary. Okay.
Okay.
You can't test the standard model to the cosmic ray physics the way you do it in the collider physics experiment. It's impossible. I mean, unless you have a gigantic detector, you place it in the upper atmosphere, and you record the event, cosmic ray event, with full details. But even then, it will be very difficult, because if you just compare the flux of the cosmic ray with the luminosity which you have at the Large Hadron Collider, there's a huge difference. So the cosmic ray physics is not, can never be alternative to the collider physics.
ये जो n e mu चीज है,
And estimator, yeah.
क्या हम ये सोच सकते हैं कि ये हमारी ही एटमॉस्फेयर की कोई क्रेजी प्रॉपर्टी है जिसकी वजह से हमें यही मिली?
I mean, this number.
क्योंकि आपका डिटेक्टर बहरहाल सरफेस पे.
If you just look at this number, from where do you get it? 25, the magic number 25. Yeah, it is basically the ratio of critical energy for pions and the ratio of critical energy per photon.
ठीक है, तो क्वेश्चन रिफ्रेश करते हैं। तो ये पायन
It's a
प्रोडक्शन
power-
ही क्यों?
Yeah,
ये पायन प्रोडक्शन ही क्यों, कुछ और क्यों नहीं?
because most of in a hadronic interaction, the most of the particles which are produced, they are pions. It's still an approximate number.
particular channel
It's still an approximate. It's not an exact formula, right? You should remember it. It's not an exact formula. This number which we have calculated, that's a based on two models. Simplified picture of the cosmic ray shower.
क्योंकि मेरे दिमाग में ये था कि अगर ऊपर से कोई हेड्रॉन आ रहा है तो हेड्रॉन के ऑपरेटर को आप एक्सपेंड कर सकते हैं उसी चैनल के दूसरे बहुत सारे स्टेट्स में। तो जरूरी नहीं है कि सिर्फ पायन आए, बगैर इंटरैक्ट करे वो हेड्रॉन उसकी यानी फेटेड हो कि वो डिके कर जाए और वो मुख्तलिफ दूसरी चीजें बना दे।
हाइड्रॉन कहाँ पर ला रहे हैं? प्राइमरी?
ऊपर से प्राइमरी।
प्राइमरी हाइड्रॉन क्यों आएगा?
हेड्रॉन तो कुछ भी हो सकता है ना?
नहीं, प्रोटॉन।
प्रोटॉन
You're talking about other than hadron.
तो कुछ भी हो सकता है।
हाँ, प्रोटॉन या न्यूट्रॉन।
मगर कुछ और भी हो सकता है।
Then what?
मसलन क्या?
For example.
मिसाल के तौर वो तो एक क्वांटम नंबर है ना, उस क्वांटम
नहीं,
नंबर
लेकिन
में आप
क्या
कुछ भी रख सकते हैं। 3 प्रोटॉन्स या एक प्रोटॉन और 2 न्यूट्रॉन्स की तरह की कोई कॉम्बिनेशन।
It's a helium. 2 proton, 2 neutron.
आप हीलियम का कुछ, हाँ चले हीलियम कह सकते हैं, सही है। तो फिर
In the
फिर भी
Corsica,
पायन ही बनेंगे।
yeah, of course the pion, because when you collide up helium, say with an air atom, so it's such a high energy, the interaction is primarily occurring between the partons of these particles. Okay? So it's just a superposition principle, global model can be used to describe this process. Exactly what we do in heavy ion collisions.
अच्छा,
So there's nothing new is there.
क्योंकि एक क्वांटम नंबर के ऑपरेटर के साथ अगर आप बाउंड स्टेट में लिखने की कोशिश करें तो आप उसको इनफाइनाइट कॉम्बिनेशन में एक्सपेंड कर सकते हैं, जिनमें पायन एक एग्जाम्पल है। जहाँ तक अगर मैं गलत नहीं हूँ तो इसका मतलब है कि डीके चैनल ओपन है और ये बड़ी इंटरेस्टिंग चीज है, सिर्फ पायन ही डीके हो रहे हैं।
नहीं, वो बात
It's just an approximation.
90%
हाँ यही
प्रोबेबिलिटी है पायन प्रोड्यूस होने की।
Actually, that is our reproduce resonance particle. The resonance particle, they also immediately disintegrate into the pions. So even then, even if the kaons or the other particles are produced, they will disintegrate into the pions. I mean, if you just look at the, for example, the what happened in the collider physics, you see what we measure. We have constructed the detector in such a way that we can accurately measure photon, electrons, positrons, muons, charged hadrons. With charged hadrons, the calorimeter has been optimized to measure the pions.
Obviously, सही।
Because most of the hadrons which are produced are the pions.
अच्छा, और ये इतनी हाई एनर्जी पे अगर इतनी एक्यूरेसी के साथ मोंटे कार्लो जनरेशन वो आपके एक्सपेरिमेंटल ऑब्जर्वेशन से कोइंसाइड करती है, तो इसका मतलब है कि आपकी जो थ्योरी है या बल्कि हमारी जो भी स्टैंडर्ड मॉडल या एक्सटेंशन का जो भी कर, क्योंकि ये सब हाई एनर्जी के ऊपर, इन तमाम में एसिम्प्टोटिक फ्रीडम मौजूद होगी हाई एनर्जी पे। ऑफ कोर्स ये तो बहुत बोरिंग है।
No,
क्योंकि इसका मतलब है कि आप हाई एनर्जी पे सब
you are talking about the primary interaction. But what about the secondary interaction?
सेकेंडरी तो फिर वो
In the secondary interaction, the hadrons will have much lower energy. And in fact, in the Corsica, we have to implement low energy interaction model. Based on non-perturbative ideas.
मैं यूं सोच रहा था कि इसके अंदर अगर डेविएशंस आती हैं एक्सपेरिमेंट में तो हम कहीं से ये सोच सकते थे कि हमारे पास बियॉन्ड स्टैंडर्ड मॉडल जो भी फिजिक्स है उसका कोई पोर्टल की वजह से कोई कुछ
No, I don't think that
यहाँ नहीं हो रहा।
this can be explored to physics beyond the standard model. Okay, I mean the reason is that what Corsica is doing is that is incorporating complexity, and the complexity is itself a problem. It's as far as the numbers which are coming from the standard model, they are the standard. We don't need them with the very precise values.
Right.
Okay, so the cross sections, decay constants, we don't need them with the very precise values. And the physics beyond the standard model is sensitive to the precision of these numbers. The real feat of the Corsica is to incorporate the complexity of the shower.
तो इसका मतलब है कि हम अगर आप ये जो भी कॉस्मिक रेस आ रही हैं, इनके जो ओरिजिन है उसको कभी भी इस एक्सपेरिमेंट से शायद प्रॉपर्ली एड्रेस ना कर सके.
No. Origin is a separate problem. The detector is not
If you can,
directly addressing the issue of origin. Detector is making some precise measurements. Like we find that this knee is over here. This knee is over here. And we can precisely tell that how the spectral index change beyond this knee or beyond this knee.
and that will in turn
That
give you
would-
information about the origin of
Yeah.
these cosmic rays.
जो हेड्रोनिक शॉवर्स हैं उसके अंदर तो मसला है ना, क्योंकि हेड्रोनिक शॉवर्स तो एक ही चैनल में मैं बियॉन्ड स्टैंडर्ड मॉडल फिजिक्स से भी उस तरह की चीजें प्रोड्यूस कर सकता हूँ जो इवेंचुअली पायॉन्स में डिके करेगी. तो हु इज डिकेइंग इनटू पायॉन्स वो हमेशा एक मिस्ट्री रहेगी. इसका मतलब है आप प्राइमरी के ऊपर जाके अनसर्टेनिटी ड्रास्टिकली बढ़ जाती, खास तौर पे अगर आपके पास 1 TeV से ऊपर की फिजिक्स है, उससे नीचे नहीं है, क्योंकि इवन आप बियॉन्ड वो स्टैंडर्ड मॉडल को प्रॉपर्ली कैप्चर नहीं कर रहे.
So there is one situation where I agree with you that if you just focus your study on a very ultra high energy cosmic ray particles, I mean, as I told you that we have the flux measurement up to 10⁻⁷, just focus on these particles, which are very rare. Okay, you will find them if you keep on. You can actually predict the flux of this. Right now I cannot tell you, but it will just to find few hundred of such an events. You may have to operate the detector
वो रेयर
2, 3, or 5
The
years.
problem is going to be calibration and all kinds of things.
Yes,
I mean,
these
how
are
are you going
the-
to understand the backgrounds for all?
Yeah.
But
to do वो कैलिब्रेट इस तरह हुआ हुआ बेसिकली.
No, what I'm saying is that if you just focus on these showers with a very high energy and test these models, then there may be some discrepancies.
No, but what I'm saying is that any such discrepancy can probably just be fudged under problems of
Resolution.
Yeah, resolution.
Yeah, but with this estimator, yeah, he's right to some extent. You first have to demonstrate that you have an estimator which can measure the energy with a very small resolution. Even 1 or 2% is enough. But first you have to demonstrate this thing. So once you are able to reconstruct the energy accurately by any method, then I think it will be a sector where you can explore these models. Probably these models will fail there. Because these models are based on the standard model, the data collected from the Large Hadron Collider, which is up to 7 TeV. Beyond that,